watching seasons change. Our roads were lined with adventure, mountains in the way couldn't keep us from the sea. Here we stand, open arms. This is home where we are, ever strong in the world that we made. I still hear you in the breeze, see your shadows in the trees, holding on, memories never change.
The silence. For some reason, the music stopped playing. But yeah, I guess it's a good excuse to start the stream like 30 seconds early. So, hello everyone and Happy New Year. Yeah, I guess it was 1 month, over a month without a live stream. So, well, no, I guess a month. So, welcome back. And yeah, today's live stream topic is going to be a little different than usual, because usually my live streams are about things I at least have some idea about. Now today's live stream is going to be about, well, electronics. And electronics is a subject which I'm actually still learning, and I'm pretty new in this. So do not expect me to be an expert today. It's basically what I'm going to show you is what I've done once and it actually worked. So I want to share it basically with you, and also if you're thinking about starting with electronics, I can give you some tips from a beginner's perspective, because you know, tips which you get from a pro and tips which you get from beginners are about different things. A pro will tell you about things to look out, which beginners usually get wrong, and I will tell more about how to learn this stuff and how I am learning this stuff and which things worked in my case and which didn't. But this is going to be in the meantime, because the main topic is going to be dumping the Super Nintendo cartridge. Actually, you know, in purpose, for example, if you want to back it up, because these things are somewhat old right now, I don't know, 25, 30 years almost of age. So yeah, dumping it and putting it on your backup isn't a bad idea, especially if we have a collection of favorite cartridges which are harder and harder to get, though still not super hard. I guess there are quite a lot of them on eBay. Now, in my short experience with electronics, actually dumping read-only memory is the thing that I found to be both somewhat easy, easy, and still achievable on my level. So it's something which you can also try without owning too much hardcore equipment, actually, and too much expensive equipment, though. Some equipment, I guess I use like that. Well, somewhat, not really super expensive though. So, today's moderator is KrzaQ. KrzaQ, thank you for being here. And if you have any questions, folks, then basically ping KrzaQ on our YouTube chat, on our IRC chat, and then, then basically he can pass the question to me using telepathic methods. Now, if I seem a little red today to you, and especially my hands will seem a little red to you today, don't worry about it. That's just the white balance I have set, because quite differently from usual, when I'm usually streaming, I do have a light set up today, which I guess you can somewhat see reflected on my face. And the light is basically to, I guess you can see it on my hand even better, like on this side. And yeah, the light is here because I do have a breadboard where the electronic stuff is going to happen, but we'll get to that. Yeah, so different lighting, different temperature, and so on. So that's why it might seem a little yellowish red today. Okay, let's go through some usual updates and then we can get going. I would like to start around 15, like 8:15. So let's try to achieve that. This is basically the view which you will get today. As you can see, I have two additional cameras set up. One is from the top, like this one is from the top, and then I have another one here which is from the side, and which I might be able to move around. And I have a light on top of that, but we'll get to that in due time. Now, I did have a browser as well. Okay, this is KrzaQ's website. Now, do I have actually my keyboard macros? Yes, I do have them. Perfect. So, dev.krzaQ.cc, and KrzaQ is known for posting frequently, and yeah, like last year. So, totally ping KrzaQ too. Like, he has a lot of knowledge in C++. We should totally be bugging him to share it with us. If it's something he wants to do, of course. Now, we actually had a mission, as you know, about, writing bots for this old tanks game, which was prepared by Firemark. And Foxtrot Charlie helped him a lot with that. And actually, Foxtrot on his blog, that would be foxtrotlabs.cc, published a post about, well, basically the results. So do check it out. The winner is going to get an FPGA. This FPGA board from us. It's I guess somewhat called an open source FPGA, which is not really true. The FPGA, the bitstream has been basically reversed, and open source toolchain was created for this FPGA. So there are some open source tools for it, which is pretty unique in the FPGA world. So this board with this FPGA is actually pretty fun to play with. I have one of these on in my collection as well. And actually, James Anton is the winner. Congratulations! And honestly, there weren't too many participants, but you know, if you participate, you win, right? So, or you have the possibility to win, and that's what James did. His bot basically was tested against the test bot, and gathered way more points than the test bot. So, but do read all the details on Foxtrot's blog. So yeah, there's that. I'm wondering what else could we have done to make the competition more popular, because actually writing bots is pretty fun, and I guess we might want to revisit that in sometime in the future. Speaking of competitions, there is another one going on, and that is a one organized by Live Overflow and me. That would be Ginvale's Winter Game Dev Challenge. It's basically a biannual competition, basically switching between Ginvale's Winter and Ginvale's Summer Game Dev Challenge, and it's a constrained programming competition with keyword constraint. This is not about just writing a game for a given topic. You actually have a lot of constraints which are of the likes, like for example, we say that it needs to run in a browser, or to be exact, in Chrome. In addition, it has to have this resolution, and quite uniquely, because we are always trying to figure out different constraints, it needs to have this overlay. And the overlay, as you can see, is basically split into two screens. There's this larger screen on the left and a smaller one on the right. And yeah, basically the game has to use these two screens. Unfortunately, the game cannot use the keyboard because we didn't know the keyboard would be there. It's like this, the competition started, and after it started, we I basically contacted a graphic artist which made the proper overlay, because there was a placeholder overlay before, but on the website. And yeah, the artist tried different things, and in the end decided that the keyboard looks here quite amazing. Actually, if I would figure out that there could be a keyboard there, or like Live Overflow would figure it out, then we could allow folks to use the keyboard. But since it was this was published like after a couple of weeks, the competition was already running, we didn't want to change the rules, and the rule is that the overlay must be on top of everything. Yeah, there are other constraints, like 125 kilobytes, so 128,000 bytes, to say it in bytes, I guess. That's the limit of how large the game itself should be, not counting the overlay image. Then 20 files or directories in total. This file format due to previous stuff which happened, and some other rules as well. Basically, the competition is going to end at the end of January, so you still, if you want to participate, you still have 2 weeks, and 2 weeks is a lot of time. You can easily win such a competition in 2 weeks. Speaking of winning, there are prizes, and the prizes are sponsored by both Live Overflow and myself, and there are monetary, well, somewhat monetary gift card prizes from the first place up to the 6th place. The first place gets $250 in form of a gift card for Amazon, one of the Amazons, or an equivalent for Steam, or in some cases that might be a gift card for another service, but yeah, we will negotiate with the winners about that. And there might be also honorary awards with $50, but yeah, we'll see, depending on how many games actually come in. I think last time we had like 22 games, so I totally hope to beat that record. So yeah, you still have 2 weeks, try it out. I totally encourage you to do so. And the last thing I wanted to brag about, basically, because this is the only way you can say it, is that my CTF team got the first place on CTF Time after the whole season. We gathered 1090 points, and actually on the Dragon Sector's blog, I've written a blog post about how the CTF season looked from our perspective, starting with Insomni Hack competition in Geneva, and basically going through China competitions, through some in Poland, and yeah, that's actually me. Anyway, through Google competition, which I actually co-organized, so I couldn't participate from the Dragon Sector with the team, but the team got the 5th place there. Through our competition and up to basically the so-called season final, the Chaos Communication Congress CTF, which is happening always in the last 3 days of the year, give or take 1 day. So yeah, if you want to take a look how it looked like from our perspective, basically do check out the blog post. And yeah, P4 was actually 3rd, which is another team. They're basically our friends from Poland, and they have a really strong CTF team. And PPP was 2nd. I'm sorry that I switched the order here. PPP is an amazing team, and it was really close. It doesn't look close, it looks like a 100-point difference. It was super close, because it's a difference of 1 CTF. Like, if we would switch, for example, if PPP would won the CCC CTF, they would be on top. So that's this kind of a difference. It's 1 CTF difference. So yeah, these guys are just amazing. I'm going to give you the link to this as well. Okay, So that's that, and we can chat about today's topic, which again is dumping or actually archiving the oh, I'm wondering if the stream is still working, because yeah, I guess it is based on the chat, because it's froze for some reason on my preview, but okay, fixed. We are going to talk about the Super Nintendo cartridges basically and dumping them. So this is a Super Nintendo cartridge with a random game. And honestly, I didn't play this game. I am a kind of a weird type of a retro fan. As you might know, my first computer was an 8-bit computer, and that was a long time ago. So I remember these times. I learned programming in the 8-bit times. I then switched to a 16-bit computer and went to a 32-bit and now to 64-bit computers. So I basically went through this. And I remember when Super Nintendo was a new thing and super cool and oh my god, the graphics and so on. So, yeah, so as far as like a lot of retro fans love the feeling of the old games and love to replay them, I'm unfortunately not really in that group. I like some games aged really well for me and I can replay them. On the other games I was like, I have this image of a perfect game from the past in my memory, and then I go to that game and it's like, yeah, the user interface is a little old school and not really easy to use, and the graphics, was it really this bad? Yeah, so that's mostly because I still play modern games. Like, I played Witcher 3 recently, then like Legend of Zelda Breath of the Wild, then like Horizon Zero Dawn, and so on and so on. And these games have amazing graphics, and then if you switch to 8-bit graphics, then it's pretty shocking. But there are games which aged well. For example, like Chrono Trigger looks, even though it looks like it is a typical Japanese RPG from that era, but the music, for example, is great, and the gameplay is still pretty cool. Apart from that, like, I played recently Alone in the Dark 1 with a couple of friends who basically wanted to beat the game in a couple of hours, which we were able to do, and that was pretty cool as well. But then there are games which didn't age too well, so So yeah, the games are not really a reason I like this stuff. I like this stuff because they had a lot of constraints in the hardware, what is available on the market, and how to create a console, a game console, for example, or an 8-bit computer, a 16-bit computer, which isn't super costly, but yet has amazing performances due to this reason or another. And the designs of the CPUs, the designs of the graphical chips, or like the I/O and so on, that's just purely amazing for me. And I really like learning about it. So that's why I got Super Nintendo, for example, because that's one of I guess, more interesting consoles from that era. Looking at the chat, I'm also more of a 16-bit graphics person than an 8-bit. I do prefer the 16-bit feel, Amiga and so on, and SNES. Now, okay, so let's chat basically what's in this thing, because this is a game, right? And it's actually a space shooter, I guess. It's called Axelay, and I must admit I didn't really play it. Now, for some reason, Nintendo decided to create their own type of, screws. And the screws are called Gamebit, and you have to get something like this to unscrew them. I'm not sure how visible it is. Basically, well, it's pretty cheap. You can get one for a couple of bucks, but you do have to order one. Or you can play with some other tool to try to open it and unscrew it. And it looks... I'm not sure if my camera will be able to focus on this at all. But it's close to normal. But not fully. So yeah, so you basically take one of these, or like put it in a screwdriver, and then you unscrew it, and and you unscrew it, and you get, I actually already done it, this thing. Yeah. Now, this thing is actually already ready for our playing, and by ready I mean it is missing a huge chip here. I will show you the chip in a second, but the chip here, which is the one which is missing, is the ROM, is the read-only memory which contains the actual game. I am not really sure what this is. I didn't really care too much about it. And there's some capacitor here and some diode, I think, or whatever. Is it a sorry, I'm not really sure what this is. Maybe it's just a resistor. Yeah, so I guess the first step, if you want to back it up, is to actually, well, desolder it. And to desolder it, I used the soldering gun, but you can use whatever. If you're wondering what the soldering gun is, let me quickly look it up, because it's actually an amazing tool. Okay, I have this one, so let's switch to desktop. Yeah, this is the soldering gun. Is basically a combination of the solder pump with a soldering iron. And so basically this element heats up, and when you press it, it actually sucks the liquid solder inside this compartment here. And this makes the soldering of the chips like super fast. We just go bzzzt, 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 and a couple of minutes and you're done. So if you're into 8-bit computers or 16-bit computers and you do desoldering of the PCBs, get this. It's not expensive, it's not super cheap, but it's not expensive either. So I fully recommend it. That was one of my best decisions to buy this tool ever. The second best decision was to buy a heat gun, because a heat gun is what this tool is for the soldering surface-mounted stuff. Anyway, so once you desolder it, you get this, which is, as you can see, I don't know if you can see. Can you see? Yeah, now you can see. It's a dual inline package. I think it has 20 pins, or how many pins do you have? Something like that. Yeah, I cannot count, but it's around anything between 24 and 22 pins. So, and this is where the game is actually located, on this little chip. Well, it's not so little actually. And it has, I guess, well, we will calculate in a second how many bytes actually squeeze in this, but I guess the question for us is how to get the data out of this. And to do this, I will be using actually an Arduino. And Arduinos are pretty cheap to get, pretty common. Like my guess is that half of you already have one lying around somewhere. And it has an AVR microcontroller, which isn't super fast and isn't super powerful, but what it does in our case, it provides the general purpose I/O output. So you can basically stick some cables here, and thanks to that we will be able to interact with this chip, and this is basically the idea behind it. But before we go there, I would like to, we basically have to calculate if we have enough I/O to actually be able to interact with the chip. As I said, the chip has quite a lot of pins, and we don't have we don't have a large amount of pins here in the Arduino, so we might want to do something about that as well. So to do that, I'm basically going to look for the chip like for this, because we don't know anything about how to chat with it either. So I'm going to look at it, at Google. Well, Google. I'm having problems actually saying this properly. I'm going to Google for how these SNES ROMs actually worked, and I'm not really sure which part of this is like SNES ROM pinout. Let's just try this. Okay, and I actually know that this drawing is correct, so we are going to use it. It's called the SNES mask ROM. If you'd actually look at this here, it has a label saying this is a mask ROM. So yeah, this is it. Sorry, and we can, I guess, start thinking about how we can interact with it. I did try to look for some data sheets, but in the end, is not really needed, so we are not going to do that. Usually what you would do, if interact with any chip, you would start looking for a datasheet if it's available. But in this case, it's not really going to be needed. So yeah, what we have here is basically groups of pins, and there are some pins called A something up to 820, and there's 822 here, and there's some other pins of this group here. The A stands for address, so on these pins you basically have to in parallel put what the address is. So you basically encode the address as binary and put it on the pin. So the bit 0 goes to A0, bit 1 goes to 1, and so on. So if we have, how many pins? Okay, I actually do need to calculate how many pins we have, because that's quite important here. Yeah, let's do that. Okay, so it has 16 pins on one side and 16 pins on the other side. How does this match with what we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so the top part is not interesting for us. We have only 20 from A0 to A19 address pins. Now, this means that we have 2 to the power of 20 potential valid addresses. 2 to the power of 20, that's 1 megabyte, well, 1 million of addresses. But we also need to check what is the word width, which is, so okay, we put in the address, but is there a byte on there? Is there a byte there? Is there like 10 bits or maybe 18 bits or maybe 16 bits? We don't know. But to do that, we just calculate how many pins we have here with D, because D is for data output. And we have 8 pins, so that means that on each address we have 1 byte, 8 bits, 1 byte, and therefore we have, we have 1 megabyte of data on this. So if you compare this to like an SD card or a micro SD card, which is like 10 gigs or something, then I guess we came a long way in the last couple of years. Okay, then we have some random things here, 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 and here. Now, GND stands for ground, so we'll have to connect ground here. VCC is for, oh, I'm missing the word. Well, for basically power, it's power supply. And then we have OE, which has a little asterisk next to it, a little star, and CE. I'm not sure about CE. We can figure it out later. OE is probably output enabled, which means that if output is enabled, then the data will be served on these pins. CE might be chip enabled. That's I'm kind of guessing right now, but I know other chips which I interacted with in the past, and I know that usually if there is an OE, that will be output enabled. If there is a C, actually C in modern chips is called CS, chip select, but chip enabled makes sense, it's probably that. That little star here means that it has inverted logic, which means that if we want to send true to yes, please enable output, we actually have to negate it and send false, like 0, send a 0, and with 0 the output will be enabled, and same with CE, the chip will be enabled when we send a 0. Now, I totally hope the C here isn't for clearing. I don't expect it is, but this is like a read-only memory after all. But modern EEPROMs are electronically erasable, so yeah, who knows? Okay, but I'm pretty sure we have this figured out. So we can basically, given that we will be interacting only with one chip, we can totally ground this, because if we connect this to ground, that means it will be tied to 0, which means, again, negative logic, that output will be enabled. We can tie CE to ground, and that way we get chip enabled as well. Then VCC goes to power. Now, SNES actually used 5-volt logic, so I think it was called TTL logic or TTL logic levels. So that's actually perfect because Arduino, I've actually chosen Arduino because Arduino is also using 5 volts. If I would go for Raspberry Pi, for example, Raspberry Pi uses a different kind of logic, and it uses the 3.3 volts or something, which would be probably the chip would not work. Maybe it would, and if it wouldn't work, then we would need some logic level shifter chips, basically, which would complicate it a little. Now, yeah, so we don't need to care about this. We just connect this to ground, and there were 16 pins on the side. That means we have 32 in total. We remove this 4 and we get 28 pins, which we have to connect. That's 20 pins for the address and 20 pins for the address and 8 pins for the data. And this is what we have to connect to our Arduino. So if we look at our Arduino, I'm not really sure we have enough of GPIO for that. Let's actually look at some pinout of Arduino. So Raspberry Pi has power output for both 5 volts and 3.3 volts, but it uses the 3.3 volt logic. I don't remember what was it called. Was it CMOS or was it... yeah, do not quote me on that. Again, I am a beginner in this, so what I'm saying, please verify it. And I will probably be reminding you of that multiple times. There's a question, does this device have a memory card? No, well, this is kind of a memory card, right? So it's a little harder to interact with, but yeah. Cool. So, what I wanted to show you is basically the pinout of Arduino. Give me a second because I actually had that somewhere on my drive. Yeah, here we go. It's actually a really nice cheat sheet. I really like it, so that's why I want to show it to you. Okay, this is from the definitive Arduino Uno pinout diagram, and if we look here, then let's look at the left side first. We have, this is not connected. This is IO ref, which, I don't know, reference voltage. We cannot use this. This is reset. So we cannot use this. We don't need 3 volts. We will need this for power and this for ground, but we cannot use this as general purpose IO, so we cannot use this for address or data. Then there is VIN, which I have no idea what. Oh, this is input voltage in case it's not powered by USB, but we will power it from USB. Which means here we basically have these pins. So these pins are actually multi-purpose, and depending on how we configure Arduino, they will be serving different purposes. There might be serving a purpose of, like, for example, SDA and SCL, that's actually IC2 or I2C protocol, but we will not be using the I2C protocol this time. We will not be using the analog, we will configure it probably as normal GPIO. So we have 1, 2, 3, 4, 5, 6. We have 6 here, perfect. And let's look on the other side. We have 1 ground, then we have, this is analog reference, which is just analog reference, so we cannot use it. But there are, looking at this column, there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16 here, we have 6 here, that gives us 22, perfect, and we need 28. So, what do we do about that? Because, well, this will not be enough, right? How are we going to connect these 28 pins to the 22 pins of Arduino? So yeah, this is the end of our stream. I will need to figure it out offline. No, not really. I will tell you one of the solutions, one of the potential solutions. There are probably many more solutions to do this. And I guess let's move to this view. Actually, this view. Perfect. So I have some additional chips here, as you can see. These are pretty random, in all honesty. I'm just using this mat to put random chips on it. But there is one here, which let me maybe show it to you on this. Yeah. I'm not sure how visible this will be. Let's try this. Maybe you can see something. I'm not sure if this can focus. Yeah, so this little chip is actually SN74HC595N, and also known as a shift register. Now, a shift register is a thing which is basically an 8-bit register where we can, using serial interface, meaning only a couple of pins, we can set 8 bits internally in that chip. Like, think of it as a variable which is only 8 bits. And we can push 8 bits into this, and it will propagate the 8 bits on the 8 pins which are coming out. So basically, just using a couple of pins, like 3 pins for example, we'll look at the datasheet in a couple of minutes, we can get several additional outputs. Only outputs, I'm only talking about outputs because the address part, we need to use 20 pins there, so maybe we can use the shift registers, because for, again, sacrificing just 3 or 4 outputs on Arduino, we get 8 outputs. For, well, we will need to wait a couple of cycles for the values to actually be pushed into this register bit by bit, and then actually propagate it into the outputs. But that's fine. We are not in a hurry. Basically, what we want to do is we want to dump this chip, but we do not care if it's going to be fast or if it's going to take an hour. We just want to back it up, right? And therefore we can afford to use some cycles. Yeah, to use up some cycles to use the serial interface into this and then get 8 additional outputs. Now, I'm actually not going to, I'm not going to use one of these, I'm going to use 3 of these, because a cool thing about the shift register is that it usually has another input, which in assembler, if you're into assembly, would be called the carry flag, which is, the bit which is pushed out of a register if you do a shift operation on it. And in this case, what that means is you can basically pair it up with another 1 and then another 2 in serial chips like this, and not adding any additional output pin usage on the Arduino, we suddenly will get 24 outputs on this. And we do not really need 24 outputs, we need 20 for the address, but that's fine. We will just not connect or like ground via the remaining ones. So yeah, but basically to know how to use it, we'll have to find a datasheet. Now, what I've learned in electronics is that being able to read a datasheet and knowing how to read it is quite important, and I actually read recently quite a lot of datasheets. This is the one for the shift register. I will show it to you on the screen. I basically have it printed from when I was playing with these registers some time ago. We can check how expensive is this shift register. I'm quite curious. It shouldn't be expensive. Okay, so this is, I need light. 74HC. Yeah, this is it. Yeah, as you can see, this is basically just $50. Sorry, you cannot see it because I didn't switch the screen. My apologies. Here we go. Yeah, just $50 for this, so that's fine. And we already found the datasheet, so we will use the datasheet to basically get to learn how to use the chip, and, well, knowing how to use the chip, when we can put it on the breadboard and start connecting cables. And when I will be connecting cables, I will just ask you folks to just go and make yourself a tea, because that will take me several minutes to connect the cables. Again, we will have to connect about 30, over 30, maybe 40 cables, so it will take some time. Okay, so, what can we read here? We can read that this is 8-bit shift registers with 3-state output. 3-state means, well, 1, 0, or like high-low, and usually it's called, I think, like high impedance, or like Z state, which is basically I personally connected with my limited newbie's knowledge as not translated to not connected. I translated to, yeah, that state to not connected. Now, this is how it looks like internally. This is basically, well, you can think of it as a register holding 1 bit. And as you can see, there are 8 output registers. Each of them is holding 1 bit. It is clocked. There is a pin for, this is internal, by the way, what's inside the chip. There is a standard reset and set pins incoming, and then there's outgoing signal. The little circle here means it's negated, but we don't really care because there's another negation here at the end of the line, and then it's outputted as QA. So the output will be called QA, QB, Q3, and QA, QB, QC, QD, and so on. Now, this is the output, and as I said, there are 8 pins of output. But apart from that, there's also another one, which is for the carry flag, which the thing I call the carry flag, which allows us to basically put in serial several shift registers like that. So if something gets pushed out from one register, it gets automatically pushed into the next shift register. Then we have some inputs. I said there might be 3 inputs. It seems here there are 5 inputs. There is this OE, which is again output enabled, and this output enabled is actually, we can just tie it to the ground probably. Then we have some other stuff, and usually what you have to do is you have to go and read about what exactly this stuff is, and it's well described in this datasheet, but and including a map of what is where, right? So these are the outputs, and this is the ground, this is the power, VCC, and so on and so on. Oh, by the way, remember my note about the asterisk in about a star denoting negative logic, and when we were discussing the masked ROM? Here, well, usually actually on diagrams, if you have a line drawn above a font, that means the same thing. This means this is negative logic. So output is enabled. That's what I said, tie the output enabled to the ground, because that will actually enable it. Now, if we go here, we can learn basically all about different timings and so on. We do not care about that yet. We might get to it later. This, however, is pretty... this is pretty explanatory about how it works, but after you actually spend half an hour trying to make sense of it. That was my impression when I analyzed it the first time. But it actually, I will be able to tell you what's going on here based on this graph, so let's use that. Okay, so as I did tell you, we have the output enabled and we are going to tie it to ground. This is going to be low, which means it's going to be 0. This is, by the way, time axis, and these are the inputs, and these are the outputs which are reacting to whatever is set on the inputs. Now, so we don't care about the output enabled, we just tie it to the ground. They are showing here what happens if it's not tied to the ground and it goes into the high impedance state, like not connected state, but that's, we don't care about that. We're not going to use that. Now, what we are going to use the SER. SER is basically for serial input. This is the bit which you want to push into the register. This is again a shift register, so if you shift 1 bit into the register, all the current values of the register are going to be shifted by 1. It works like a normal shift operation in programming, actually. And to actually make sure a shift is going to happen, you do need to raise the serial clock. This is the serial clock. And on the rising edge of the clock, so here, this is the rising edge, it will read the state of the serial line. It will determine, hey, it's 0 or it's 1, and then it will put it in the first series of registers. As I showed you above, there are the output registers and there are the input registers. And when you shift stuff into it, it is being put here, like first in the first register, then you shift it to, it's going to be shifted to this register, and then your value will come here, and so on. Now, when you want it to appear on the output, what you need to do is you need to let's go to the nice diagram again. And as you can see here, it basically, the edge went up and we had a 0 here. This is a 0, this is a low position, so it's a 0. But the output didn't change. It was something, unspecified something, but it didn't change. And it didn't change neither when there was another rising edge here, and it again queried what is the value here, and it was actually a 1. And again, nothing happened. And this is because to push the values from the input registers into the output registers, so they are actually visible, you need also to send an R clock signal. I'm not sure what the R stands here for, but if you do basically on a rising edge, all the input registers are going to be propagated to be latched into the output register. So this is the rising edge, and as you can see here, the output starts to, like 1 came last, so it's going to be here. This is the 1, the same one actually is this one. And the 0 came earlier, so it was here, but then it was actually shifted. So this is the 0, and then the output was set to 0, right? So this is the 0. Yeah. So this is basically all we need to know. We do not care about the serial clear. The serial clear is if you basically set it, then it will clear the register state, and we don't really care about it because we can just, it's uninitialized in the end, but we'll just push enough bits to actually make it initialized. So we will probably tie it to VCC because it's negative logic. We do not want it to be stuck on clearing. We do not care about this pin. So yeah, we do not care about this pin. We do not care about the other pin. We only care about these 2 pins. One will be used to send the data. One will be used to actually say, okay, now read the input pin and shift the registers. So this is the serial clock. And one will be used to actually latch, like assign the output registers with the input registers. If you're late here, basically what we are doing today is we are dumping a Super Nintendo card. Well, dumping as in backing it up because this stuff is old and we might want to back it up. So we want to dump this little ROM chip into our PC. And we are going to be using Arduino for that, and I need shift registers, which I'm explaining right now, to get enough I/O out of Arduino, because Arduino only has 22 output pins and we need 28. So that's why we are using this. There's a question on chat if there is Q3K. I could check on IRC. You should check, but yeah, Q3K is basically the hardware master from Dragon Sector. Like, if I ever get stuck with hardware, I just go to him and I ask him. It doesn't happen too often, in all honesty, because I prefer to be stuck and figure things out myself. But sometimes I cheat on it. I just go like, hey, KrzaQ, help me with that, or what do you recommend doing in this case? He's absolutely amazing with hardware. Okay, so we basically know what to do. Now we need to connect it. Now, there's another question here of how fast is this? How fast can we go? How fast can we go with Arduino? And actually, if you look through the datasheet, you will find different timings, basically. For example, like switching characteristics is one of the things you might be interested in. And depending on what we will be using it around 5 volts. So you can, and this is the model we are using, and it's in nanoseconds. So you can basically read the values here. And sorry, if I think there are like 2 tables with this stuff. So these are the switching characteristic, and this is the timing requirements. Yeah. So if we, for example, when we set stuff up, we put the data in the serial pin, right? And then we need to, well, raise the serial clock, to make sure that the data is actually latched into the registers and the registers are shifted. And this tells us how many nanoseconds we have to wait. And we have to wait holding the serial before using the clock around 25 nanoseconds. So if you're if 25 nanoseconds doesn't tell you anything, don't worry. I'm also trying to wrap my head around this, but it's like this. 1000 nanoseconds is basically 1 microsecond. 1000 microseconds is 1 milliseconds, and 1000 milliseconds is a second, so that means that there is 1 billion nanoseconds in a second. So 25 nanoseconds, it's actually, if you would convert it to frequency, I think it's 40 megahertz or something like that. But obviously this is not the only time delay we have to guarantee. What I'm going after is that, you know what, Arduino isn't super fast, especially if we are going to program it in C, and we are going to program it in C. It's not going to be super fast. We probably do not even need to care about the timings, because whatever is written here, Arduino will be slower anyway in the way I program it. So we will probably not be introducing any sleeps or too many sleeps into the code, because it will be just handled just by the slowness of Arduino. If we would, on the other hand, take an FPGA, a fast FPGA, then we probably would need to care about the timings and make sure that the timings are met, because a fast FPGA might be working at, like a decent FPGA might be working at like 50 megahertz or 100 megahertz, and in this case, this stuff starts to matter. Yeah, so okay, so basically that's it. Now what I need to do is I need to set up the breadboard, right? And to do that, I will have to keep this on my screen, because I need to know what I'm connecting. There's this little notch, as you probably know, on the chip, which tells you, this notch here, which tells you where's the top of the, and where is the first pin, thanks to that, of the chip. This was supposed to be an arrow. Okay. So yeah, basically the idea is that I will connect Arduino to serial. I will connect Arduino to arc log and serial clock. I will tie this to like 5 volts. I will tie this, maybe I will figure out what to do. And I will tie this to ground, and I will connect these into the address pins of our ROM chip. One more thing which I want to check, because again, there are 20 address pins on the masked ROM, which we will be interacting with. And then we will get 24 outputs from 3 serial registers put in, 3 shift registers put in serial, which means that 4 will be not connected. And I'm wondering if I have to tie the not connected ones to ground, for example, or if it doesn't matter, because sometimes it does matter, and sometimes if you do not do that, then things start to get funny. But I kind of think here it should be okay, just not to connect them to anything. Okay, this is a detailed description overview. It's probably somewhere here. Okay. Yeah, the logic levels should be fine here, by the way. This is how to connect it. They are using a capacitor, a decoupling capacitor here. I'm not going to use a decoupling capacitor because, I mean, we are just going to dump a ROM, not using super high frequency. The power should be quite stable. We can always run it a couple of times. We don't care if there will be any caps on the chip, so yeah, I'm just not going to put it there. Normally in my, I don't know, like PCB design or whatever, I'm totally putting every cap which is advised by the manufacturer, but in this case I'm just going to skip it. Then, okay, layout. Oh yeah, this is exactly what I was looking for. So if we have unused input, we need to tie it to VCC, but we have output. Oh, this is what we care. Why do we? Oh, that's weird. Oh, it's written here. Inputs should never float. So this is important because, well, we don't plan to have any floating inputs anyway, so that's fine. As I mentioned, we will tie the output enabled to ground and the other one, the clear, to VCC, so that's fine. Does it say something about the outputs? Can the outputs float? Float, by the way, float means unconnected. So if, yeah, that's electronics for you. It doesn't mean floating point units, it means unconnected. Okay. It is generally acceptable to float outputs unless the part is a transceiver. It's not a transceiver, so we will be... I'm just not connecting outputs. That's what the datasheet says, so I'm going to believe it. And yeah, that's about it. I don't think there's anything more interesting here for us. There are some more, like, for example, if I would be creating a PCB and for some reason, well, this is a standard dual inline package, a standard DIP package, but if for some reason it wouldn't be standard, then this is super useful to make a footprint for the PCB, and it's quite fun actually as well. I've done one for my other boards, for my VGA boards. And this one, like this 15-pin VGA input is actually a footprint I made, and it actually worked, which I'm super happy about. Perfect. So we basically get to the moment where I ask you folks, do yourself a favor and grab some food, go and eat something or whatever, because I'm going to need to connect 50 wires or something. So I might be talking through that time, but I will be focusing on connecting it here. So wish me luck. And basically when I'm done connecting, we will go back to writing an Arduino program to basically be able to, well, to dump it. Now I need a couple of more of these chips. If you cannot hear me, by the way, let me know, because my mic is hanging there and this stuff is over here. So, okay. Yeah, this is another one. And this is another one. Perfect. I'm actually not really sure what other chips are here. Yeah, they're pretty random. Now, I do have quite a lot of cables. I do have this set of cables, which is... open it. Yeah. Which is basically came with a breadboard, which I have here, and I'm going to try to use it because they don't take too much space. Then I have this set of cables, and if I run out, I have some additional cables. And then if I run out and I don't have like 50 cables, I will basically take apart one of my projects, which I have somewhere there. But let's see what happens. This is basically a pretty standard breadboard. It's pretty large. There's a model here. I bought it over 10 years ago when I had one of my first attempts to learning electronics. I usually use smaller breadboards, but for today I decided to just go with this. Now I'm not going to play with Arduino yet. I am going to put this here. If you're not familiar about how a breadboard works, it's basically just a quick introduction. These, and like there, as you can see, different columns here. There's this column, this column, this column, and like for example this column. Now the small columns, the pins here are connected in a vertical line. And this is basically a power bus, the small column here. This is a power bus with one column being like one column of pins being for ground and the other being for whatever power you need, right? And then the other columns are basically connected. 5 pins in each row are connected up to the gap, and then there's a disconnect in the gap, and then there are 5 more connected, make a group. So 5 pins here make a group. And yeah, so if I put like my chip here, I'm going to put it here, or am I going to put it here? Yeah. That means if I, for example, want to connect something to this pin, I just put like the output in here, which, yeah. And that's basically it. So it's just for prototyping. Okay. I'm probably not going to use too many resistors. I actually don't, I'm not going to use any resistors. I don't think I need to use any resistors here. Now I need to put these somewhere. So which direction am I going to put them in? I'm going to scroll up to the datasheet with how the pin layout works. Okay, so the output is almost uniquely on this side. So this is what I'm going to do. Can I put it here? Yeah, barely. I think it will work. Okay. Yeah, it should fit, but okay, here we go. So this is one, then another, and the last one. And make sure that they go in the same direction, basically. Okay. Perfect. Now, I guess I will start with power, and in this case, I need to connect VCCs to the lower pin on the right. So this pin, and this pin will have to go to VCC, which is again the standard power. And yeah, I'm wondering which one. Excuse me for not using proper coloring in this case. In today's project, I would probably be using totally random colors, but I'm not sure I have enough colors, like for example enough red wires to connect it properly. This isn't connected to power obviously yet. I will connect it later on. So let's just put it here and connect it here. Okay, so this is one power, this is the second power. Maybe two. Yeah, I want to basically bridge it together later on with the other, so I'm going to skip the first one. Again, everything in this column is tied together. Okay, this is fine. Okay. So this is for power for these chips. Now I'm going to power this as well, but I do not have, where's my pinout? Okay, here's my pinout. So the power is also on the top. Oh, that's cool. But I'm wondering which, oh, okay, now I have to use this one. So it goes here and here. Yeah, maybe it's too long, but whatever. Doesn't matter. I mean, this is low frequency stuff, so whatever. Now, okay, I'm just checking if there are any questions. So this is the power. Now let's connect ground. Ground in this pin is here, bottom left. So bottom left, perfect. Where's the nearest? Okay, so here is the nearest ground. This is way too long. Okay, and okay. Ground and ground. Okay, perfect. Then I will have to make the same thing with the chips. The chips have, where do they have? They have the ground also on the bottom left. Okay, it seems to be some form of a standard, I guess. Or maybe just a lucky coincidence. Here and here. Yeah. Okay, here and here. Yeah, seriously, if you want to order pizza, do it now, and it will arrive by the time I'm finished. Okay. Yeah, this is fine, fine. Okay, so we have a ground. Now, I did tell you already that I'm going to tie some of the pins to ground and some of the pins to power, so let's do that. In case of the smaller ones, of the shift registers, I'm going to tie... I'm going to tie output enabled, I guess, and yeah, output enabled only because we need to serial clear to tie it to VCC. So output enabled is pin number 4 from the top on the right at pin number 13, and yeah, so is there any easy way to tie it to the ground? Okay, so it's pin number 4 from the top on the right. 1, 2, 3, 4. Here we go. Yeah, power is crossing with ground. That should be fine. Maybe I'm going to use smaller ones. Alright. So 1, 2, 3, 4. Oh, in case it isn't obvious, never do rewiring if you have this connected to power because you will fry your stuff up. You might also learn some interesting things. For example, if you short like 3 volts with ground on an, what was it, a Raspberry Pi, I believe, then it resets the Raspberry Pi and a couple of connected things to it. Yeah, don't do that. Okay. Forward. Okay. Okay, this is tied to the ground. Output enabled is tied to the ground. That's good. And I need another one. Okay. And this is also... Okay, so output enabled is tied to the ground. Now I'm going to go back to the SNES ROM chip. There's also output enabled and chip enabled, which I need to tie to the ground, so I'm going to do just that. And to do that, it's top second, actually. So this one, and I want to tie it to the ground. Okay, it's tied to the ground. Then I need to, it's 6th from the bottom. No, wait, I'm looking at the wrong thing. No, I'm looking at the right thing. 6th on the bottom, from the bottom on the right. It also goes to being tied to the ground. So 1, 2, 3, 5, 6. Okay. Yeah, I don't like cables crossing over each other, but whatever. Let me just count again. I'm a little worried here, but I will get something wrong. Okay, 6. This is 6th. Perfect. Now I had to tie to VCC the serial clear, but would be pin 11. That's in these, all of these 3. That would be 3rd from the bottom on the right. And I do need to tie it to high. High as in VCC. 3rd? No, 3rd. No, wait. 2nd. It's 2nd. Okay. So 2nd tied to power. Yeah. Then 2nd tied to power. And one more 2nd tied to power. Okay, that's fine. So I have these now. I need to basically, tie the serial input to. Well, no. I'm going to need to connect to the serial input of the first shift register of this one. Arduino will be connected there. But the second one, the QH thingy, which is, here. The QH thingy will be connected from the first one, will be connected to serial input of the second one. And then the same thing, the second one's QH dash, not dash, QH apostrophe will be connected to serial input of the third one. So that's what I need to do. Okay, sorry, let's go back to this view. Perfect. So, okay. how to do that in a decent way. Which pin is it? Is the last pin here, and I need to connect the last pin here to the third pin in the next one. So okay. Last pin here connected to the third pin here. Can do the same here. Last pin here connected to the third pin here. Yeah, again, apologies for crossing the cables. Just I want to do it fast. And then here the the output can be, because this Q apostrophe QH apostrophe here will be floating, it's not connected to anything. We can leave it floating according to the datasheet as we read. So that's fine. Then we need to connect serial here to Arduino, and I'm actually going to just go with it somewhere high and connect it later. So that's the third one, and the third one is going to go here. So later on, I'm just going to connect Arduino like to here, and this is going to be the serial input. Because it's lying here, right? Then, okay, so this is the serial. Now, what about clock? The clocks are going to go at the same time, kinda at the same time to all of them, which means I need to connect them. Well, connect the R clock to all R clocks, and then connect that to Arduino and connect the serial clocks as well. So the R clock is fourth. Okay, let's start with serial clock. Was third from the bottom on the right. 1, 2, 3. Okay, this one with. Okay, this is way too short. Do I have longer ones? Not really. Yeah, I do not want to switch to the other cables yet. Let's use this one. Third one from the bottom, correct? Correct. 1, 2, 3. This is the second, because it's connected to clear. Oh, this is okay. Third one, 1, 2, 3, not connected to anything else, correct. And then I need to connect the same one with the one here, third one. And then I need to bring it somewhere high that I can connect Arduino to later on. Okay, so let's do it here. So yeah, so this is going to be the serial input, this is going to be the serial clock, this one. And now I need, you know what, I'm actually going to stick cables there already. Yeah, it's just, how long will I need it to be? Maybe this will be fine. Okay, do I have longer ones? Whatever. So yeah, let's stick this one here and this one here. Basically as a reminder for me to later stick them into Arduino. Perfect, now I need to connect the R clocks, which is the fourth from the bottom. And I'm running out of this length of cables. Now I still have a couple. Okay, so fourth from the bottom, I connect them together. So this is fourth from the bottom, and then this is fourth from the bottom connected together, correct? Fourth, double checking, yeah, that's it. And then again, fourth from the bottom connected to 1, 2, 3, 4. Yeah, oh, come on. Okay. And 1, 2, 3, 4, perfect. And then I need to connect that to, yeah, again, like bring it somewhere at the top of the board here and squeeze another of these cables there, like for example this one. I do not want the same color. Yeah, I know I'm not using any color coding, but okay, and this is the R clock. It might be a good idea to actually note it down somewhere. Let me open a notepad. So cereal was what is that color? I don't know. It's like violety red. Well, let's call it violet for lack of better name of the color. Then serial clock is the orange one, and the R clock is the green one. Okay. So this is noted, and I hope it's correct. This goes to the 4. Yeah, it's correct. Okay, so we have the Arduino connected. Now we need to connect the serial out. Well, we have the Arduino inputs connected. Now we need the shift registers to be connected to the chip. And the first, so we need to basically, yeah, this is what I'm looking for. I need to have it somewhere popped up because I need to see the image. I'm actually going to, yeah, maybe let's just leave it here like this. Now, Windows, do not attempt to help me. Let's do this and then open the best, like the best application for graphical editing ever. Okay, let's just move it here. Perfect. Now, so I'm going to do a screenshot of this. And also I'll be putting it to Paint. So I have them like next to each other. Okay. Now I can continue. I'm going to, basically what I'm going to do is I'm going to use the first one, right, and connect QA to address 0, QB to address 1, and so on and so on. And then when I run out of registers with A8, I will use the next shift register and I will connect QA to A8, QB to A9, and so on until I run out of pins basically to connect to. Okay, let me maybe switch this here to this view again. And I don't know, is it too dark for you folks? Let's maybe do this. And I'm going to use these cables, I guess, for it, because yeah, it will be quite a lot of quite a far distance. So QA to QA of the first register, which is this one. QA the second pin, correct. Come on. Okay, it works. And I need to connect it to the fifth one from the bottom. This is ground connected. This is data 2, data 1, data 0, and then we have address 0. So I connect it here. I'm actually going to connect it. No, I'm going to connect it here. Let me do the count again. Yeah, that's fine. Okay, so this is the first one, 19 to go. Okay. Then I have QB, which is this one. Okay, and QB goes to A1, which is here. Okay, now I have A2 and I have Q3. So this is quite easy. Can I do it in a way that... No, well, whatever, doesn't matter. Okay, then I have A2. No, but sorry, A3 to... Yeah, it's just going fine. So just do this in a somewhat automatic fashion. This, the next one. And the next one. Until I run out of pin, basically, which is going to be in 1 pin, 2 pins. I'm doing it in a, without looking, which means I will have to verify it in a second. Let's use this one. No, this is broken. Or is it? No, it's not really broken. Okay. And here. Perfect. Now, how many pins do I have left at the top of that chip? I have 4 pins left. Having 4 pins left means, wait, 4, yeah. 1, 2, 3, 4. Everything is connected fine in that case. So this is the first 8. Now I need to connect the second 8. How do I get more pins out of this mess? Sorry, more cables. Okay. So QA, we know is here on the second pin, correct? Correct. And it goes to A8, which is, how many pins is it? Output enables 1, 2, 3. I think it goes to this pin. Does it though? Yeah, it is. Perfect. Sorry. Got kind of tangled up with this. Okay, then QB is here. And I'm going with it to A9, which is just beneath. Then I'm going to A10, which for some reason is here, and then I will have to left, correct? Correct. Okay. Next one is 811. So it's here. Yeah, the pins aren't really in order, I guess. 812. Where's 812? Oh, it's on the other side. Here. Then A13, which goes actually here above the yellow one. Okay. A14, same drill. Okay. A15 is also here on the left side. Okay. And that's it for this shift register, which makes sense because A15 means we already used 16 out of the pins, so yeah. Then next one is a second pin. Second, correct? Is this second? Yes, it is second. We connect to A16. Where's A16? It's in between of these pins, which I already have connected. Okay, perfect. Now I need a couple more cables. A17, which is on the top. So here, the first one on the top, correct, goes to the one on the very top of this chip. Not the masked ROM. Perfect. I'm going to check if there are any questions. Can you do DOCSIS reverse engineering analysis on wire? No, because I have no idea what's that. I'm sorry. I did tell you, if this is related to electronics, then I'm a noob. If it's not related to electronics, then I don't know what's that. Sorry. Okay, I'm going to stick it here next to it. So that would be 18, and I'm missing a 19, which is on the top here, the very top. Yeah, the very top. It's not connected to anything. Correct. Perfect. And okay, then there are 4 outputs here which are not connected to anything, and we are not going to connect them. And that's actually it for connecting the chips. I need to, well, we still have the data outputs, but I will need to connect them straight to Arduino. And then what we are missing is the, what are these? Oh, this is the data. Okay. What we are missing is connecting the power lines basically with each other. So let's do just that. So, yeah. Which power lines are we using? We are using these ones. So connect this one to the plus to plus. Yeah, it's not great to have it sticking out of the board, but whatever. Plus to plus. And I am not using these two. Perfect. Then I need minus to ground basically. And another one ground to ground. Okay, so I have this connected. Now I need to connect Arduino to it still. So let's start with that, maybe with ground. Okay, this cable will do. Oh, I'm sorry. Here we go. Ground, and then where does Arduino have ground? I did have a really nice looking diagram of Arduino pinouts. So ground, I guess we have the ground somewhere here, right? On the top, yeah. From the bottom, it's the third one. Oh, and in this top segment, it's the third one and the second one. So, okay, let's connect to that. So this is ground connecting to, hopefully ground. Third one in the upper segment of connectors for Arduino. Maybe move it a little. It's ground, perfect. Now I need to connect, yeah, I'm sorry about the color coding. Again, I have pretty random cables. So probably this should be ground, maybe other, but whatever, it doesn't matter. Like, colors don't change anything, it just makes it more confusing for anyone. If it would be a normal project, I would choose proper cable colors, but it's just dumping of a ROM, which is, I will, take apart later on. And 5 volts are here. Yeah, so this is the 5 volts connector, perfect. Now I need to connect the... what do I need to connect? I need to connect these 3 here to the Arduino, which would be, this would be serial. Where do I want to connect them? This is the analog input. Trying to make sense of these, of the markings on the diagram. Can I connect them in a way that, yeah, I can. If I connect data here to the PC0 to PC4 and 5, oh wait, is it duplicated? How is it? Yeah, it is duplicated. These are the same pins here at the bottom and here. So I don't have 22, I have even less. I have 20 outputs on the Arduino. Well, whatever. It doesn't matter now. Okay, I want to connect to one port so I can somehow easily get the data. So, okay, I will connect the data here, which means I will connect the serial stuff here. So that would be, yeah, let's just go with this one. Maybe, like, I'm going to connect the serial and clocks to these 3. What does this mean here? Does this mean that it's connected to a pull-up register by any chance? What is it? I'm pretty sure like these ones are connected to pull-up registers, because if you're going to I to C, like I square C, then you need pull-up registers, so these might be connected to pull-up registers, but on the other hand, I'm not familiar with what the other stuff is for. Yeah, I don't know. If we run into... Oh, PWM. We don't care about that. That's fine. It's just connected there. Then the orange one, let me maybe switch the view. Here, and the next one here. So this is for the shift registers. Now for the data input, I want to use this bank here at the bottom, and in proper order, so I can just read a byte by reading one register in Arduino, which shouldn't be too problematic here. Oh, but I am going to need longer cables than that. Do I have any long cables? I'm pretty sure I do, actually. Or maybe I have shorter cables. Yeah, I think I have shorter cables. In that case, I need to move Arduino a little, but I don't want to put it on this metal thing. Let's move it. This is not great, to say the least. I'm sorry. Okay, so PD0 is this one. And I need to connect it to... Oh, I have no idea what I'm connecting it to. Where's my paint? Here's my paint. D0 is here. Alright, it's here. Next one, I'm going to connect to D1. Which is this one. And it goes here. Maybe I should just turn it the other way around. Maybe a little closer. No, because I need to. Whatever, let the Arduino stay here. I'm pretty sure it's not shorting anything. I am going to. Okay, this should be fine. Sorry for that. This was one. Now, where's my other? Second one. Can you see the Arduino? Yeah, you can still see it. Then data 2 goes here, and this is the last pin on that side. When I'm basically plugging this in, I'm also trying to make sure that I'm not plugging twice into the same pin unless I really want to, or need to do it, because that's, you know, some proof checking going on there. Then I have, yeah, it's going to be a little tight here. So that's, and a couple of more cables to go. Then I will basically double check it, and we can start damping the ROM. Now the whole idea behind damping the ROM is basically that we will push the address to the shift registers and then allow the shift registers to push the address to the chip, and then wait, and then so the chip actually, you know, fetches the data and propagates it to the output, the masked ROM, right? Sorry, and then when the masked ROM does it, we will read the data back, and we'll do it byte by byte until we get the 1 megabyte of data, or how many data is that on the chip. I think that's 1 megabyte, right? Okay. Okay. Couple of more. So that's, yeah, 2 exactly. Perfect. I'm counting how many cables we still have to, like how many pins we have to connect, and because that's a checksum basically, isn't it? And it seems to match. Okay, that's fine. And the last one. Okay. Yeah, I guess it's needless to say, but I will anyway. Not all ROMs work this way, right? The older ones maybe work this way, the newer ones are usually clocked or usually use some SPI or whatever protocol. Will I be writing my own dumping sketch for Arduino? Yeah, I will be. It's super short. That's a good question, but I will be writing my own code to dumping it. Perfect. So now let's quickly double check the cables. I'm going to clean up my desk a little because it's in cables basically. Cables everywhere. Or wires, not cables. I'm sorry. Okay, I think it took around over half an hour to connect the wires. So if you ordered a pizza like I told you to do, then you already have your pizza by now. Or at least I hope. Yeah. And this episode is not sponsored by your local pizzerias, your local restaurants. Perfect. I need to see the Arduino first. Power and ground, because this is the stuff which fries our stuff. So 4th pin here, 4th pin on this side, counting from the bottom. Yeah, 1, 2, 3, 4, 5 volts. 5 volts. It's connected to the plus, and this is connected to the plus, and this is connected to the plus. Okay, this is fine. Like the 5 volts connections are fine. Then ground. Ground is the 3rd one. It is correct. And it's connected to ground. Ground is connected to this ground here. And it's connected to the ground, which is here. Which is also correct. Then, yeah, the serials are connected on, the shift register is connected here. Which is fine. These look like typical. Yeah, these look like typical I/O pins. Then the data is connected here, which everything is in the PD bank, which I hope it will be visible as one register, one global variable inside Arduino. If not, then we can, do some bit manipulation, but whatever. I don't want to do it if that's not needed. I'm wondering what is this. TX connected to Atmega and used for USB program and communicating with it. Really? Does that mean that I cannot use these? It is a good question. Can I use these pins? Yeah, I'm checking basically. Yeah, I probably do not want to use these pins, but I can use these pins. Should be fine for me to use these pins. Let's see what happens. If it doesn't work, then I will switch pins. Easy. Grzegorz writes that a New Year was some time ago, but let's see the fireworks. Yeah, that's pretty possible. Okay, so let's see if the file works. I do have a USB cable here. So I'm going to connect it, and then I'm going to quickly disconnect it in case of smoke coming out, because smoke is not desired and is not part of this exercise, so please no smoke. Okay, Arduino connected. I've heard that it connected through the headphones, which is fine. Now let's see if Arduino got detected by... I'm checking if my breadboard is not shorting anything, but it's not perfect, like the edge of it. Cool, so let's jump here into the code. Okay, I do need a new Arduino. I'm going to use the standard Arduino IDE, because why not? I know that there's a command line version nowadays, which wasn't there some time ago. It's pretty new, I guess, from last year, right? Here we go. I hope I didn't close the diagram, though it's going to be needed. Okay, now it has one thing loaded, which is blinking. Can I zoom? Yeah, I can zoom. Okay, so this is blinking. Let's see if blinking works. Because if blinking works, that's fine. You cannot probably see it. Let me make it a little smaller, the window. But it detected the Arduino, which is good. That means it's not frying yet. Okay, I'm compiling and it uploaded. Let's see if it's blinking. Yeah, there is a LED here. You probably do not see it. But let me maybe turn down the light. Yeah, you should be able to see an LED blinking right now, which is here. I'm going to turn off the light. Totally. Now it's obvious that it is blinking, right? So the Arduino still works, which is a good thing. And that means we can actually play with it. So let's make a new one. Okay, and I'm going to, thank you. This is my old code, which I did for testing, but I do not need to save it here. I hopefully will not have to look at the code, but in case I fail the code, I will look at it, just to make the stream shorter. Now, live stream. And the new episode. Okay. Here we go. Okay, put up setup code here and then main code here. So what we need to do, or maybe it will be fine for us to use these pins because it will be just input for us. Sorry, let me switch back here. Okay, sorry, here we go. Perfect. So now, now what I do usually and almost always is I basically Google for how to do this stuff. Arduino configure GPIO. Pin mode. This sounds about right. Whatever. Yeah, just go away. Okay. So pin mode, and this is digital pin as output. Perfect. This is exactly what we need to do for all our pins. Now, I could use the datagram. How are the pins numbered? These are, I guess, the numbers of the pins. So what I need to do, oh, actually, let's look at, let's check it for the blinking LED. Here is the blinking LED. And it has like LED built in, which tells me absolutely nothing, and to output, whatever. Pin mode. We are setting 2, 3, 4, 5, 6, 11, 12, and 13 as, I do hope this is the correct way I'm thinking about the pins. Digital pins page. Pull up. Okay. The problem with this stuff and the same with Raspberry Pi is that there are different nomenclatures, how you count pins. And I do hope I'm counting them correctly. So, yeah, whatever. Let's assume these are the pin numbers. sorry. Actually, you know what? I'm going to check what LED built-in is, and this should allow me to basically figure out what if I have the correct pins. Okay, so LED built-in is 13. If we look at the diagram, 13 is here, and it also has a LED connected, but it's 19 here, so we need to... I thought we were supposed to use these ones, but we have to use these ones. So that's fine. Okay, it's good that I checked. I would use the incorrect ones, and... oh, ID, it's even... yeah, if... sorry, you don't see that. It's even written down here if I would just read the diagram instead of guessing. There is... Justas or Justas? I'm sorry if I mispronounce your name. Check that it's also double-check that it's that number 13, which is correct. What I found out. So okay, in that case, yeah, we can use a for loop. For I don't know. Can I do this like? I think it's normal C, or normal C++, but I'm not really sure. Or equals 7. I++, we want to set up the pin to be input. And we want to hope it will work. Then we take the other pins which are on which are here, like 8, 9, 10, which will be the way we control the shift registers. So that will be I can just do this. I don't know what I'm going to, in this case, I'm going to go for pin, sir pin, what was the other one? Serial clock, and then the R clock. Okay, and first, looking at it from the bottom, we have the serial, so that would be 8, then the serial clock is 9 and 10. Okay, so we set pin sir to output. And yeah, I don't think we care about any pull-up registers or anything like that. If it will not work, we will figure it out. Okay, so the pins are configured. Hopefully it works. I'm not super sure it will though. And then put your main code here, and this is running in a room. Now, before we get there, I actually want to also initialize the serial console, because if we do not initialize the serial console, we will not have no way to get the data back. So how do you know serial print? Yeah, that's fine. And is there an example? There's an example. Yeah, this is basically what I was looking for. What this does is basically it allows us to communicate over the USB, and this actually spawns a question: which pins is the serial using? Is this using the pins I think is using? Because connected to Atmega and used for USB program, which pins are used for the serial output? I believe I did check that some time ago, and I think this will be these pins actually, so our code might not work. To double check it, we can do something like this. We do serial begin there, and then we can output something like serial print ASDF, and then serial print programmer not responding. Why is it? No. What's up with these errors here? Just new line, and let's see if this works. I'm going to compile it and upload it, and I want to open the serial monitor. Yeah, and it should output ASDF. Does it work? No, it doesn't work. Why doesn't it work? Oh, it's still thinking. Okay, it says blah blah blah, doesn't work. Access denied. Why is it? What? Now I'm going to just like disconnect it. Sorry, close it and then run it again. Pins 0 and 1 are used for serial. That's what the person says, sorry. Eustace. Let's assume this is how you pronounce it. Do let me know how you pronounce it. Yeah, I also thought these are used for serial, so which means I need to reconnect my stuff. And to reconnect my stuff, I'm going to disconnect the Arduino. Okay, disconnected. And I'm going to move my 2 bottom pins to these locations. The Misomosi, for the one which are used for SPI, I guess. So that would be 11 and 12, and this is where... I didn't want to go this way, but okay. So 2 bottom, 1 bottom, and 2nd bottom are going to be moved in the same order. I hope in the same order. What was the order? Where's my paint? Okay, so this one is... no, this one is first. Here. Okay, so this means we need to change stuff. Now I can reconnect my Arduino because I turned it off. Okay, it's reconnected. And now I'm going to run, this has Blink again, so I'm going to upload Blink again. Okay, and it's blinking, fine. So open recent, our sketch. Let's not, no, let's actually like just do it properly. So int short whatever, and like data pins maybe. And now the number of the pins where we have the data in the order which the data is actually there, which would in our case mean that would be 11, 12. That's the, on 11th is the first bit, then on 12 is the second. And then we have, well, easy, 2, 3, 4, 5, 6, 7, right? That makes total 8, perfect. So, for, I could have left it like this. We modify data pins. This, and then we try this again, okay. Do it and also show me the monitor. Something's still not working. Done uploading, but I do not see any data, and this is supposed to be run in a loop. How is this? Wait, I have this the speed, no line 90. Oh yeah, it works now. Perfect. So you can see it works. I'm actually going to hide back. No, sorry, this is not what I wanted to do. So it works, which is perfect. Now we can continue because we are getting serial output. And apart from that, I think we have everything set up. So now we need to do 2 things. We need to first push the address into the serial, the shift registers, right? And then after we push the address, we need to wait a while, like stay a while and listen, basically, you know the drill. So let me do basically send address, shift registers, address, and then we are going to put the address here. So it's going to be, does it have like a student page? That would help me a lot. Int 32, because the address will be 32-bit, and that's the address. And we'll send an address. So yeah, let's not print it anymore. Send address, basically, and some address. We are going to do it in a loop, but so and 32 address, starting from 0 and up to whatever is 2 to the power of 20, which we will handle just by using bit shift. And then we need to increment the address by 1. So we send the address. And then we wait, basically, but we don't need to wait because, or do we need to wait? Let's not wait and let's see what happens. Because as I said, Arduino isn't going to be super fast, so I don't think we need to sleep here too much, in all honesty. Yeah, if it doesn't work, I'm going to change it. And then we need to receive the data, so like get byte. Or read byte or whatever, and this is going to be to byte, and well, okay, B. Now let's see if this compiles, because I'm not sure. Okay, so what does it say? It says left shift is, oh wait, here, unsigned long, really? Okay, so that's fine. SR get byte was not, yeah, that's true, it wasn't. Okay. Yeah, okay. So it totally accepted my standard int, which I was wondering if I can use. Given that I can use it, I do need to, like, Arduino is a platform where an int, I believe, is 16 bits at most, which means that if you want to use 32-bit variables, they will be unsigned long, or at least a long, but I'm using unsigned long. Or maybe is it a long? Let's actually verify it. I'm quite curious. Yeah, it's just a long, so unsigned long is fine. Okay, then we send the byte and we get it, and then when we get it, like, we need to print hex. And we want to print hex the address. Or do you want to print the address? No, we don't care about the address. We want to print hex the byte. And at the end of it all, we want to go into an infinite loop. Yeah, this is an infinite loop. And we want to say, like, how was it? Serial print done. Yeah. Okay. And now, having done this, we need also another function, which is the void print hex. And we get a byte, and we need to print it as a hexadecimal number. Actually, there is a print hex, or like Arduino can convert into hex. How was that? How did you do it? Inner print hex. No. Print. Oh, I like this. So, but there's a gotcha here. This prints hex, but if you give it only 1 digit, it will print only 1 digit, and we need actually 2 digits. So let's make sure that if x is lower than 10 hexadecimal, in that case we actually do print like a 0, and then we serial print. And by the way, we want to do like serial start. Yeah, here, some markup. And then we print the value, so like this. Is that correct? It is correct according to Google, which is perfect. If it's larger or equal to, it's basically 2 hex digit, then we just don't care about the first line. And it will, this guarantees that 2 digits will be printed out. Okay, now we need to push the, oh, let's read the byte first. How do you get the input of, Yeah, as you can see, me programming in Arduino is actually, it's just like reading the manuals or actually Googling for stuff which I know how it works. I don't know how it's called. Okay. Eustace says that I have to make sure to select correct board and bootloader version. Yeah, that's actually should be fine. And also, if something is connected to pins 0 and 1, then this can disrupt the upload, which is what I expected. So yeah, I'm happy that we actually reconnected the pins. Eustace, thank you for your hints. Actually, it's really useful. Now, yeah, getting the bytes. So there's a byte which we need to get, and let's call it B, and 0. A byte consists of 8 bits. And for every bit, we actually need to do something like this. B, we add a bit. The bit we get from, I do hope this actually gives us 0, 1. Yeah, we get the bit from, what was it? Was the name? Data pins? Yeah, data pins from I, and it will be either 0 or 1, so we shift it by I. And that gives us the byte. So, okay, we can read whatever is put there. Now we need to send the address. And this is again the thing where we need to basically do this dance, right? And the dance goes like this. We need to do this 20 times basically. So 20. We do not care about the 4 remaining registers, bit registers, because they are not connected to any outputs. We do not care about them, therefore. On the serial, so we do digital write. On the serial pin, we output a given bit of the address, and we start, because it's going to be pushed every time, which means we need to start from the top bits. So we send the top bit of the address first, and then it's going to be shifted 20 times until the end. Which means I need to do address shifted by I, which is not correct. Shifted by... address shifted by 20 minus I. And the first case is going to be 0. It's going to be 19, right? Yeah. So 19 will give us the top bit, then if I will be 1, that will be 18. 18 will give us the second top bit, and at the end it's going to be 19, so 19 minus 19 gives us 0, so this is perfect. So we're going to put that on the serial lane, then we need to basically raise the clock. So we raise the clock, and we can actually, you know what, we can lower the clock here. So lower the clock, send the data, raise the clock. Again, we are not caring about the timings at this point. If something is not working, I will add some sleeps. But as I mentioned, Arduino is so slow that the shift registers are way faster than it, and it can totally support it. Okay, then... so that's that. And then when we do everything, then we just do the same thing, but with the R clock. So we use the R clock to basically, we put it high here, and this will commit all the input registers into the output registers once we have it set. And that's it. That will, yeah, lower the clock. Here we lower it, then we send on the serial with serial clock all the 20 bits, and then we raise the R clock to commit it to from the we commit it from the input registers, and we latch it into the output registers, so it will be available at the output, which is connected to the address line, which should be fine. And let's see what happens, basically. Let's see if it compiles. Now, I did have a monitor. What happened to my monitor? Hello, monitor. Upload. Sorry. It outputs some data. I'm not sure if the data makes sense. It doesn't seem to make sense, in all honesty. No, I don't think. Now what? doesn't make too much sense. I'm going to actually, after every 16 bytes, sorry, I'm going to make a new line. So if address and let it like figure it out itself, then and I'm going to start with like just get me the first 256 bytes. Sorry. Wow. Sorry, I'm used to pressing Control L now because that's like synthesis in Quartus. Whatever. Don't I need... Oh yeah, I totally need it. Here, you are totally correct, but what I'm missing here is this thing. Depending on how the digital write works, it might be not needed or it might be needed. So thank you for pointing that out. I think Tomer on the chat and yeah, Tomer and ABC spotted it, so well done. Okay, and upload. Okay, this doesn't look so bad, actually. Right, my typical mistake, I always do it. How did you... There was an easy solution to it. Was it address +1? Yeah, I think it was address +1. I'm just guessing. Okay. Okay. Actually, like looking at this, it kinda looks like real data. It doesn't look like... It might be gibberish, but it might be real data as well. Let's dump everything. Clear output and dump 1 megabyte. Verify or actually compile. Root 0, thank you. Best of luck in the Winter Game Dev Challenge if you're participating. Okay. And it's dumping. Yeah, I could set the serials a bit higher. You're absolutely correct. Let's try. Let's see how fast is it. 11522. And let's do. Oh, it actually can do even more. Perfect. And upload. X41. Thank you for the idea, but actually will save us a lot of time. Okay. Yeah, that's way faster. Yeah. Basically, it's dumping. It's not blinking or anything, but it's reading data from this stuff. I wonder if I, like, by moving this cable, if I actually I actually destroyed our dump, but I hope not. Yeah, this totally looks like data. It's too... There are too many zeros and it's too random to be... Oh, not data. And the Fs were... Yeah, it's totally data. We are dumping the ROM, which is great. Any day now. I hope I actually... well, we'll see. Okay, once we have it dumped, we will have to basically create a dump file, like dump hex file, and then convert it to with some Python script into data, so we can start writing that script, let it finish dumping, and like count for something UI. The script is going to be like super easy actually. So this is dumping, and we are going to write with open hex, dump hex, and we basically need to read it. We don't care about binary as f. Open, not f, read. Alright, so we read everything, then what do we do? We basically are going to do something like this. It's going to be slow, but we don't care because it's only 1 megabyte. So it's going to be fast anyway. like relatively slow, but in absolute, speaking in absolutes, it will be fast. Replace. We replace this with an empty string. We do the same with done. I believe it's a done exclamation mark. Is that correct? It is a done exclamation mark. Perfect. And then we do the same with like end of lines. Like this and the other one. I'm not sure this one even appears, but whatever. And then we do d equals d decode hex. And we dump it with open dump.bin. Write binary this time as f write d. Okay. Now we need the data. Why is it not dumped yet? Well, we can calculate how long will it take, right? Because it's dumping at this speed. This is in basically in bits, and we like wait. Do we have a bug somewhere here? Is it dumping the same addresses over and over again? How much data do we have? I don't want to stop it. But it did work. Yeah, I'm having some problems with... Is this actually working correctly? Because I kind of have a feeling that it's dumping over and over the same thing. Let's stop it. Let's dump the first 1 kilobyte and see. So I'm going to reset. I hope it clears the output. Clear output. Yeah. Okay, so it works for this. Let's test if our code works. Because it took way too long. Then I'm going to conf set code. Okay, and then if I look at it from the... Yeah, I don't know. It might be data, it might not be data. Okay, so let's dump more data now. Then let's dump 15 bits worth of data. That's 32 kilobytes. Yeah, okay, so that's that. Okay. And let's look at the dump. Doesn't look great, but okay. Now we kind of know how long it took, so let's try 17 bits, so that's 4 times the amount. But with 17 bits, if there's any shenanigans going on around the 16th bit, with this actually being converted into an infinite loop, we will learn that here. So. I'm checking if we are correctly dumping stuff, but we are correctly dumping stuff. I actually have this ROM already backed up. But I guess having the data we already have at the end of it, yeah, there is a string with the name of a game. So we are correctly dumping the data. This has been confirmed. So maybe instead of actually waiting for it to finish, there might be some... Oh, wait, yeah, there's probably some infinite loop here. Why is there an infinite loop here? I'm pretty sure my code is correct unless it's doing something funny around this, not respecting the size of this. So, you know what? I'm going to do something different. I'm going to basically tell it, hey, please print the size of uint32. and let me know. Oh, it did finish. So it's fine. We can just wait for it to finish everything, but we are not going to do that because I already have it dumped. So yeah, let's just play with that because we know it's working. Therefore, we can just test it. So I'm going to change the file, bin, okay, yeah, and I guess we can just run it anyway, because I would like to still check if we have the correct dump, but it will take, I guess, 10 minutes or something. I'm trying to figure a way to make it faster, but nothing comes to my mind apart from compression. And I don't want to implement compression, and it's not going to be necessarily faster. So, yeah, assuming that it would work, let's see how the game looks like. I do have some SNES emulator, I believe. I do, perfect. And this is the dump file. It's a unknown file extension. What's the correct file extension? It's probably ROM, isn't it? No. Okay. Okay, and yeah, show me what you have, basically, all the files, and this is this. Okay, yeah, so it works. It's still dumping the rest of the ROM, right, but this actually works. I don't want any sound, please, no sound. I guess it's... So, I guess this is it for this episode. Let me know actually what you think about it. What you think about the idea of me giving you some info dumps about what I've learned, because this is different from me, again, knowing the subject. I actually have no idea what I'm doing, and it's just that I've done it a couple of weeks ago, and I found it fun to share, because I always wondered myself how to dump a cartridge, right? How to back up this stuff. And then, yeah, I don't know, just archive it. So, do let me know what you think about these type of streams, and if you want to see more hardware, more electronics, right? Or if this is you don't like the idea, and basically I should stick with CTFs or programming or whatever. So do let me know, because I'm actively learning this stuff right now, so I might have some other similar simple ideas to show in the future. So yeah, let me know. And also let me know how the setup worked. Did you actually see anything? Because I do realize that this camera here, if I have my hand here, you do not see anything, and I probably should have the camera on the back instead, so you'd have a better view on what I'm putting where. But well, I guess this is the first time I've done it, so that's that. If you have any questions, yeah, it's still dumping the data because I want to verify if my old dump is correct regarding, the new dump which we did. The next, okay, so Tone suggests that maybe the next session should be about altering the code of the game and uploading something to the ROM. I'm not sure if I could actually upload stuff to this ROM. It doesn't seem to have all the pins which are required to reset it and write again stuff there. So I would have to figure out a way to emulate the ROM, probably with some FPGA or whatever, right? And this sounds fun to do. And I actually have some plans to do some cartridges like that for a couple of platforms. So maybe later this year we can actually do what Tone suggests. Okay, so Chris says that mask ROMs are not programmable. Yeah, there might be just written in silicon, let's call it. On the other hand, there also might be just like they never, it might be reprogrammable, but they never made the connections, the output pins to do that. But I do believe Chris in this case. It's probably way cheaper to make a masked ROM, like not reprogrammable. The ROMs are read-only. You'd have to put a flash chip with compatible pinout. Yeah, so X41, you are absolutely correct. I do not believe there would be a compatible pinout, especially that I don't think flash ROMs are like flash memory. Sorry, is using parallel interface, but maybe I'm mistaking. Again, it's probably easier to just do this stuff using an FPGA or whatnot, but that's well, we can chat about it at the end of the year. Okay, I think that's about it. At least I don't see any other questions. So it seems the chat, you actually liked it. So yeah. So I'm happy actually about that. I know I'm a little bit chaotic about how I'm presenting this because this is a first for me. Yeah, I'm still kind of waiting for it to finish, but yeah, I'm not going to upload the ROM, by the way, because yeah, I guess Nintendo wouldn't be too happy about that. And again, I'm doing this for the purpose of backing up the cartridges which I own, and not for the purpose of dumping the ROMs on the internet. And I do not believe that you could actually dump the ROM just watching at my like live stream or having the video. The stuff changes here too fast to do an OCR on it. Use the F macro. What does the F macro do? I'm curious. Okay, so do I have my browser somewhere here? Okay. So F macro means... What does it mean? Does it put it in the flash memory? I guess if I don't use the flash, the F macro, then it doesn't put it in the... sorry. How does it work? Sorry, I'm going to actually like grep for it in the libraries of Arduino. Okay. Oh, this is not going well. Yeah, but I do see that actually in the example code of some stuff, folks are using this macro. Oh, here we go. Okay, so F string literal interpret cast, flash string helper, and something p str string literal. So flash string helper, what are you? Okay, it's not helpful. Okay. Now I guess it's defined in a different file. Did it finish dumping, by the way? I'm still kinda... No, it's still going. It probably places the string in the flash memory instead of placing it in line with the code. I'm wondering if it really makes a difference. Okay, well, it's still going, so let's not wait for it. So thank you for today's stream. Thank you to KrzaQ for being my moderator today, and I guess that's it for today. If you have any questions, do let me know. Apart from that, I would like to. Oh, it's finished. It's finished. Yes, let's do it quickly. I already lost my herb, as you could see. So here conf, okay, converted, and I'm going to basically compare it using Total Commander, like with my old dump, and as you can see, yeah, it worked. We dumped the ROM correctly, so it's basically the game you saw. So that's it. Thank you for being here tonight. Let me know about your comments, and see you next week or tomorrow if you actually speak Polish. Again, thank you to KrzaQ for being my moderator today. And yeah, that's it. I will send you the source code. I will put the source code on, I guess, on my GitHub, because why not? But it's not terribly complicated, but I will do it anyway. It will be on the stream en directory with the number of the stream, which is 70. That's it. Thank you for today, and see you next week. I'm going to leave you with some music. Bye bye.